Welcome to Securing Digitalization, the Siemens cybersecurity podcast. We have done everything they've always told us to do. We have different passwords for different applications. We make them really complex with a lot of question marks and weird characters and dollar signs and whatnot. Then they told us to switch on two-factor authentication, and we've done that. And now they're telling us our passwords could be hacked in the next decade or so because we're getting these super powerful quantum computers. I want to figure out, what is quantum computing? Why could it help folks to hack our passwords? And I'm very lucky because I have two people who spent a lot of time and effort to understanding not just cryptography, but also quantum cryptography. Here are Hans Aschauer, a physicist, and Fabrizio de Santis. He studied engineering and cryptography. Both are senior cryptography experts at Siemens. Hi, Hans. Hello. Hi, Fabrizio.
Hi, Andreas.
Hi, Andreas.
So help me a little bit. We're talking about quantum computers. We're talking about cryptography. Let's do it step by step. What is a quantum computer?
Seems to be so easy, but actually it's quite complicated.
Hans, I'm braced. I'm buckled up for it.
A quantum computer is a computer which works by completely different means than classical computers. And because it works in a completely different way, it can do certain things much more efficient than a classical computer. For example, it can break many of the cryptography that we are doing today.
What specifically can quantum computers do so well that the computers we're using today for our recording that they're not so good at?
If you multiply numbers, this is not very difficult. Everybody of us knows how to do it. What is difficult if you give you the product of two numbers? It's quite hard to find out which the numbers were, at least if the numbers are large enough. And even classical computers, our best computers that we have, the supercomputers that we have, cannot do this if the numbers are large enough. Different for quantum computers, they can do this. So they can solve this difficult problem. And actually, this is one problem which is used in one of our most used crypto algorithms called RSA for the experts. So if the quantum computer can solve this problem, it can break RSA.
RSA, that would be protocol that's used to encrypt my communication, say, with my online banking or if I encrypt an email?
Yes, exactly, that is. If you look at your web browser and you have in the top left this lock and you see it's closed, quite often RSA is one of the two options that exist today. If you have an ordinary lock, locks are constructed typically in a way that it's quite easy to close the lock, but very difficult to open it if you don't have the key. RSA crypto system is similar to this lock in the sense that everybody can close it, but only if you have the correct key, you can open it.
And this key is secret. I make it complex, so it's harder to crack. And imagine tomorrow somebody built that quantum computer that can actually hack RSA, crack my codes. What would be the consequences of that?
If you think of the very simple explanation that I gave you, it would be equivalent to not only someone being able to break my lock at my door, but then it would mean that out of a sudden, all locks all over the world would not be secure any longer. This is now in the cyber world, not in the physical world. But even if it's in the cyber world, it has quite important effects on our real life. For example, if your bank account is empty out of a sudden, or if someone breaks into a train interlocking system, bad things could happen to trains and something like that.
So it would be the equivalent of a world where all the doors, the physical doors to which I have physical keys, suddenly they're open. All the locks stop working. Any door is open.
Exactly.
Okay, so financial crime, people might empty my account, they might read my email. And you also mentioned this example with trains. What's the issue there? Why is this also important for a company like Siemens?
Yeah, at Siemens, we are not that much interested in keeping bank accounts secure. I mean, this is also obviously an important thing. What we are doing is we build cyber physical systems which operate at the edge between the cyber world, so the computers, and the physical world, like trains, for example, like power plants, like building automation systems and stuff like that. When the cyber world becomes insecure, this means that also the physical world becomes insecure because bad things can happen then.
So in a way today, Fabrizio, what I hear from Hans is a train is not just a train, pieces of metal and other materials welded together. It is coming together with the software side. You can't really separate the two. And if the software becomes vulnerable, then the whole thing is vulnerable, Fabrizio.
Yeah, this is true, Andreas. Cryptography is basically used in many Siemens products, from automation, trains, buildings, basically everywhere where data must be stored or transmitted securely. And protecting confidential information, this is something that we do in our daily communication, so by the means of encryption. This is just an example. However, integrity plays an equally important role, since we want our systems to exactly behave the way they are intended to act. And if an attacker would be able to manipulate a system like a train, then a train could be set on a wrong track, for example. And sometimes we are really talking about life and death situations, and this is something we want to avoid and need to avoid as much as possible.
Okay, deviating a train, that could be risky. Any other examples you can think of?
On a different scenario, for example, electric charging station for electrical vehicles is something that is on the way, that we will see in the next years upcoming. And of course, as Siemens, we need to be sure that the payment system will work correctly. So when you charge your car, and on the same way that the person doesn't get injured by charging an electric car, these are all things that comes together in our systems. And we, from the cryptographic point of view, we need to ensure that there is no problem at the cryptographic level. And for this reason, we are trying to build our systems secure at the cryptographic level, and of course to have multiple level of defense in order to avoid such kind of possible attacks.
It sounds a bit like a doomsday scenario. Maybe within a few years or a decade, all our passwords could become useless, but that's a big maybe. Aren't you maybe exaggerating a bit? We're not there. Quantum computers are not yet that powerful.
We as cryptographers are really paranoid. At least that's what people say about us. But the question is not if we are paranoid. The question is if we are paranoid enough. Why is this so? I mean, even if it could happen that for some reason never a quantum computer can be built, we have to be prepared. We cannot wait until the day that the quantum computer is really there. So we have to try to see into the future, into the foreseeable future, and prepare for what could happen. Because the consequences, if we are not prepared, are really, really bad.
It sounds a bit like how the world is preparing for potential impact of meteorites. It's very unlikely, but if it were to happen, it would be catastrophic. So just get prepared early on.
Yeah, actually, we already have quantum computers. They are even connected to the cloud, and they can be easily programmed and accessed by anyone. It's just a question when we will get cryptographically relevant computers. So this is the open question. And in this respect, I would like to mention that post-quantum cryptography can also be seen as a new type of cryptography that can be useful anyway. And additionally, it will protect against quantum attacks in the future. And therefore, it must be seen as an opportunity for us to switch to a new type of cryptography, maybe even in combination with the old one. And this is something that may be also due to regulation that will come in the near future, in the near or mid future, because of customer requirements that we might have in the near future, customers asking for this type to support this kind of cryptography. So this is like a new toolkit that we have in our hands, and we have also to understand how to use this kind of cryptography in our use cases.
Sounds like a bit of push, a bit of pull. Clients will ask for it, say the train operator from your example. Also, you mentioned regulators, Fabrizio. Who is seeing the world the way you're seeing it? Which governments, which regulators are already pushing towards better encryption, future-proof encryption?
So we have announcements already in 2015 from the National Security Agency in the US, the NSA, but we have seen similar announcements to migrate to post-quantum cryptography also from other security agencies like the French one, ANSI in France, but also here in Germany, the BSI, the Federal Office for Information Security, has issued similar announcements, advices. And we have also seen some governments, like in the US, the White House has also published an information sheet advising the government system to migrate it to post-quantum cryptography.
You both work for Siemens. What is the company now doing with that push and with the pull from clients? What are we doing now with the need for future-proof encryption?
Our role is to evaluate the recommendations in terms of their impact on our products, because post-quantum algorithms will have in general different requirements and sometimes even different interfaces to deal with. Although this is typically not a problem for a general purpose computer, this may be a different story on embedded systems, and many of our products have little computing power and perhaps only one battery. And we need to understand how this new type of cryptography, namely post-quantum cryptography, will affect our and future products.
So just to make sure I really understand this, what's going to happen is that the attacker, if it's a quantum computer, has huge computing power for that very task of breaking that lock. And what I heard from you is fine, if you have a modern computer that can deal with a very large key, for example, to protect its lock. But what if it's a tiny device, maybe a tiny little mini computer sitting on a shop floor or in a train, for example? That's more difficult. It doesn't have so much brain power. Is that the point you're making?
Yes, of course, we need to evaluate and understand which is the impact of post-quantum cryptography even on those little tiny devices in order to come up with the new requirements for future products and be able to support this kind of new cryptography in our products in the future.
How much time, Hans, Fabrizio, do you think we have? How many years do you think are we away from quantum computers making my existing passwords useless? Just each one of you, give me a number. How many years? What do you think, Hans, Fabrizio?
My crystal ball tells me 15 years.
15, Fabrizio?
Oh, I will say beginning of the 30s.
So more like 10 years. You're even more pessimistic as far as the lifetime of my passwords is concerned. Now, you brought us a graphic, and I like it a lot because it makes it clearer what needs to happen for quantum computers to make my passwords useless. So what do we actually see on this graphic, Hans?
Yeah, on this graphic, we actually see two different lines. One is going up and the other is going down. The line that is going up shows us over time how the size of existing quantum computers increased. It started at 1 qubit some 20 years ago, and nowadays we are roughly at 100 or 200 qubits.
So for those of us who don't know what a qubit means, it's like a way to measure the power of a quantum computer.
Exactly. In a kind, the storage capacity of a quantum computer.
What would be the equivalent of a qubit with our current computers?
It's hard to compare, but in a sense, 1 qubit is, in a very specific sense, 1 qubit is equivalent to 1 bit.
Okay, so one decision, if you will. Yes, no, 0, 1. So they're getting faster, okay? And so that's one line. That shows us how quantum computing is becoming more powerful. What about the other line?
The other line, the decreasing line, shows us how many qubits are required in order to break, for example, the RSA encryption system. And this line is going down because algorithms become better over time.
What I hear from you is today you might need quite a few qubits to crack a existing password, but the algorithm, the programs are also getting smarter. So the computers are getting more powerful and the effort needed to crack my encryption is becoming less and less.
Exactly, that's true.
Okay, so at some point these lines meet, and what I heard from you is maybe in 10 years, maybe in 15 years, maybe a bit earlier or a bit later, but still it's 10, 15 years. Why be so alarmed? Can't we just see how this evolves and in 5 years' time maybe start making reasonable, resource-efficient plans to cope with that?
Yeah, this would be great if we had that much time. Actually, we have not that much time. For example, if you nowadays encrypt something using RSA, someone else could just record whatever you have encrypted and send over the internet and wait for 10, 15, maybe 20 years until a quantum computer exists, and then use the quantum computer to decrypt what you have encrypted. And if the secret is still of value for you, maybe if it's health data or something like that, then you would be very embarrassed. Whatever you sent over encrypted line would become known to anybody else.
So in a way, it's too late to have stronger post-quantum encryption. By the time quantum computers are ready to crack my codes, I need to encrypt at that super high level with post-quantum encryption before computers are able to crack my codes.
Exactly, that's the case. This is one of the reasons why we don't have that much time. Another reason is, for example, for Siemens, our products stay in the field, stay alive for many years, for decades, for 20 years, something like that. And if these devices are not prepared for this new kind of crypto, for post-quantum crypto, it will simply not be possible to update them. And for that reason, we also have to think about this kind of crypto, this new kind of crypto today. And it would be far too late if we started thinking about it when there is one quantum computer that can break the encryption.
So a Siemens train in a couple of years, ideally you'd love for it to be delivered already with post-quantum encryption.
Either that or at least being prepared for post-quantum encryption so that it can be updated in a secure way later on.
Okay, so Fabrizio, that's a lot of work for you, for the colleagues who build the products, for the customers, the clients who use the solutions. But once we're through, maybe in 5 years or 6 or 7 years, then we're done, right? That's going to be a huge effort, but then we're done, Fabrizio.
Yeah, not so fast. We need to migrate devices and
Yeah.
infrastructures to post-quantum cryptography. And
Yes.
this migration may also not happen in one single step. So we need to prepare our systems to be migrated multiple times, probably, because different issues may arise in the future as well regarding both cryptographic algorithms and implementations.
Sorry, just to make sure I understand this well, it's not going to be that we, in, say, 5 years, have perfect post-quantum cryptography and then we roll it out and everything's smooth. We might stumble into this new world, try things out, and then maybe our devices, they don't really cope with it. There's going to be a lot of learning involved.
Yeah, exactly. So cryptographic algorithms also need a lot of time to be investigated. So the security thereof, we need to understand whether they are really secure as they claimed, and there are no problems in the algorithms and no problems in their implementations thereof. So it can also be that there will be a bug, a problem, a security issue in the implementation of a new cryptographic algorithm. Therefore, we need to be prepared and also design our system to be more crypto agile, so to support crypto agility by design, meaning that we should be able to change cryptographic algorithms also because of state regulations, for example, multiple times in the future. And this is now a different situation that we have to face and to deal with, because at the present time, cryptographic systems were kind of monolithic. So it was and it is difficult to swap, to exchange cryptographic algorithms because they are the core of security. So we made our system always to be very monolithic in this sense, while in the future, we have to make them more agile.
An analogy could be up until now, using RSA, it's like we're all using physical metal keys and have metal locks. The future might be, we might use key cards with a magnetic stripe, or potentially we're going to use an iris scanner, or maybe both, we just don't know. And that's crypto agility. I can use different methods in the future.
We will need to use different methods in the future. We will need to have multiple locks, maybe organized in different ways, maybe one within the other, or maybe just use two of them in parallel. We need to be basically prepared to use multiple cryptographic algorithms, probably in different use cases. And this is now a completely different situation from what we have seen so far.
It's a bit like in these gangster movies where in the first scene you see the senior banker trying to go to the vault, and then he or she needs first a key card, then a key, then the iris scanner, and finally setting a number combination on a mechanical lock. Lots and lots of different layers. That might be the future of encryption.
It might be, and it will be fun for us.
By the way, talking about fun, both of you have dedicated years and years and years of your life onto the topic of encrypting, building locks, and of course that includes the idea of how to crack them. If you think back, what has been the most fun bit for both of you working on cryptography? Who wants to start?
The most fun bit for me has been when I was able to break an implementation of the RSA crypto system using a photographic flash.
How did you do that? It's just light, right? How does light crack an RSA algorithm?
Yeah, sounds impossible. And that's why this was so much fun. You can use light in order to make the computer to have it miscalculations. So it does just a few bits flip, the calculations are wrong. And now what you do is you encrypt twice, once using without the light, and you get the correct result. And the second time with the light, with the flash. And there you get the wrong result. And then by doing some mathematics, which is not that difficult at all, you just break the key.
So in the case of Hans, the biggest fun was actually breaking things, not protecting things in the first place. And then Fabrizio, what was the biggest fun moment for you?
Yeah, I have to admit it was a quite similar experience as for Hans. So I was participating in a group where we were trying to attack a real product and trying to extracting a key, a secret key, but in this case was by electromagnetic field radiation. So a similar technique to that one used by Hans, but also different one. And in that case, seeing the key to be extracted so easily from a real device on the other side made me thinking, as a designer, what can I do to prevent this situation? And also it was pretty impressive for me to see how cryptography could also actually be broken quite easily by physical means. This is something that people doesn't think of at the beginning. So it's quite spread the idea that cryptography is hard to break mathematically, and this is true. But when it comes to implementations, then the situation is the other way around. It may become very easy to break implementation of cryptography to achieve the same goal, so to extract the secret key. And this is really an experience.
So I get it. You have two souls, each one in you. One is like move fast and break things, but your actual purpose is to move fast and secure things. And what I take away here is that, yes, my passwords are safe today, but this will change with quantum computers. We're all getting ready for it. And it doesn't matter whether it's just to secure online banking, for example, or to secure industrial operations. We need to start now to get ready for the post-quantum world of cryptography. Big thanks to both of you. Hans, Fabrizio, thank you very much. Vielen Dank. Grazie mille.
Thanks for having me.
Thank you, Andreas.
Thank you. Take care. Bye-bye.